Okay, we are going to discuss chemical bonds now, specifically metallic bonding. Quick reminder, metals, we know, want to give away electrons to have their full valence shell. In order to become more stable, the easiest, the most direct way is to give electrons. So the goal, again, is to have this full valence shell, but sometimes there's no nonmetal present. If we don't have a nonmetal, then metal atoms have a particular behavior, the way that they hold together in a solid form. What these metals will do is they're going to donate their valence electrons into a sea of delocalized, okay, so not local, freely moving electrons that surround the metal cations. So here's a look at that. We're going to have this metal, let's say gold, for instance. It has these valence electrons, and it's more stable if it doesn't have that outer energy level with its partial grouping of electrons. So it can give these electrons away. It can't permanently attach them elsewhere, right? It's never going to be a true ion here, but what it's able to do is kind of shrug off the electron, push it away into a vast sea of other electrons that are just kind of freely moving off doing their own thing. Now, because of this behavior, a few things happen with metals. So these electrons, if you attach an electrical current to them, okay, if you put a current to, let's say, a metal wire, what happens is you get a very clear flow of the electrons. They offer a clear path for electrons to move from one side to the other, and you end up with the positive and the negative regions separating as they will. Another product of this free moving electron sea is that heat can also be transferred very quickly. So our electrons are going to take the kinetic energy, the heat, from one side, and they offer another path that's very clear, very simple for the heat to transmit from one side to another. Lastly, what we find is that despite the metal cations not wanting to have these outer electrons, if they push them away, then our slightly positive atoms, these slightly positive nuclei, are going to attract those free-moving valence electrons that you see all around the sides. So those layers of metal, if you try to pull apart metals, you'll notice they're incredibly tough. They're hard to pull apart because of those positive-negative attractions. However, these electrons can slip by each other, okay? So you can cause them to sort of shift, and they obtain a property that we call ductility. They are ductile, which means you're able to form wires from them. So this is a look at that. You can see this linear shift of our very, very ordered, structured, positive cation set. Now, I'll let you take a second, go ahead and do some of these practice problems. I'll assume that you've now done that. In metallic bonds, electrons are able to freely move. A term that we use to describe freely moving electrons is we say they are delocalized. Why are metals able to conduct electricity and heat so well? It's because the electrons move freely. They offer a path. Okay. Now, what term describes the ability to stretch a metal into wires? And this is ductility, the ability to stretch a metal into wires. Metals, we describe them as ductile. Okay, so ductility is that behavior.